Thank you for joining the latest in our structural engineering series. My name is Matt Williamson. I'm here to introduce our speaker today, Derek Jacobs, who will be speaking on the structural repair strategies. Derek is our structural engineering department manager. He has been with ADF for 14 years. He's licensed in quite a number of states across the country. How many, Derek?
Probably about 26, 27.
More than half. All right. Thank you, Derek. So if you have any questions during the presentation, please type them in the chat window and I will ask those questions to Derek at the end of his presentation. And with that, I will hand it off to Derek Jacobs. Take it away, Derek.
All right. Yeah, thanks everybody for taking time to kind of sit with us today. This is, I think, hopefully a little bit of a fun topic, even though it's, when these items and issues come up, it's never a good, for you it's never a good time, but hopefully we'll cover some interesting stuff, see some interesting pictures today, and kind of figure out what you can expect when you see stuff like this and what you can expect to happen as a result. So that's kind of what I want to talk about. We're going to learn about different types of damage and repair, what those repairs would need. We'll kind of go one by one through, when we walk down a site as a structural engineer, what is the most common to maybe least common types of issues that we find, and then what are those associated repairs that go with it. And so hopefully by the end of this, you might be a little bit equipped yourselves to, when you're at these sites every day, being able to recognize some problems, and if anything, give you, an idea of when you want to call in some help from an engineer to help you address some of these issues before they get out of hand. Or, we want to talk about prescriptive methods. If everything's easier to repair right away and then waiting for a long time, letting it get worse. Same with anything in your house or your car. If your check engine light's on too long and you just keep ignoring it, those repairs are going to get more and more costly. So we want to look at all these things. The guidelines I'm kind of going to be referencing a little bit, and I mentioned I did take a couple pictures from both of these documents, so that are pretty helpful. The first one is the AISC, which is the American Institute of Steel Construction. Their design guide 16, which is actually a new version, just came out, governs or pretty much addresses the assessment and repair of structural steel in existing buildings. So a lot about what we'll be talking about today. And then ACI, which is American Concrete Institute, their guidelines 546. It's kind of the same thing on their end, which is Concrete Repair Guide. When we both of these address just not only the repairs, but also the assessments and determining what kind of damage we're going to be looking at and what the issues are. And so they cover a lot actually too about testing and really getting into the forensics of what you're dealing with. And that's a little bit more, they go in a little bit more depth than we do. I think, when we go to a site, our first step in the assessment is going to be collecting that information too, which includes dimensions and shapes, steel shapes, dimensions of beams, lengths, the strength of the materials, and determining what the original design assumptions were for any structure we're looking at, which is to say, and I'll repeat, if any of you guys were here for my very first webinar, which was the basics, kind of structural basics 101, the one thing I always try to encourage everyone to do is to keep your structural drawings. It is a very valuable tool for an engineer coming into your existing site to be able to take a look at those. And sometimes I know they get lost. It's hard to keep track of them over 20, 30, 40 years, but knowing what the original intent and everything was of these buildings is very valuable. Kind of going into a little bit about that right now. materials, and the reason that is material strengths can vary by the age of the building. The strength of what we're looking at can impact our strategies, and also even potentially what the weldability is between different types of metals. For the most part, any of the facilities that you guys are working at or that we're visiting are pretty modern and are built with either A36 or A992 steel members, but occasionally we'll get to a site where it's much more like an earlier historical building. You can see if you go back far enough, you can get into wrought iron, or even cast iron, and that's when you start to get into weldability issues and different kind of issues with the repair strategies if you have to deal with that. Concrete and rebar strengths have also changed over time. The yields, the strength of rebar is much stronger now than it used to be, and the kind of your basic concrete mix is also increasing, and as we kind of develop those technologies. So we make assumptions based on the age of the building, kind of following this table here when we don't have the drawings, but having them available is great. So the first kind of damage we're going to talk about is probably the most common one, which is corrosion and weathering. And in regards to steel, we see this quite a bit. I'm sure a lot of you have seen it as well. Obviously, it's just the same. We're talking about rust. A lot of our stuff is outside. A lot of it's exposed to the weather all year round. There's a good table here that I pulled from the AISC guide that kind of gives you a average corrosion rate for unprotected carbon steel per year. A mil, for reference, is 1/1000th of an inch. So even at 2/1000ths of an inch per year, that's per surface. So if you have like two sides of a plate, and it adds over a course of 30 years, obviously that adds up to quite a significant loss. If we have a 1/4 inch flange in Cleveland, of a beam 1.5 mil per year after 42 years, that beam's lost about half its strength, right? So some of these sites are that old, and this is just this table just shows common wet weather cycles, but as we all know, facilities, these environments can be much wetter than normally anywhere else, and constant, and they corrode much faster. So when we're talking about beams, a little quick structural lesson here. We want to look at the behavior, and when we're trying to assess how significant damage is or how concerning a certain amount of damage is, we'll look at the behavior of the beam. So if you have a beam with loading, obviously in the middle, even if it's point load, if it's a distributed load, generally you can assume that the amount of bending is the highest in the middle, right? We have this load here, and you can see when you do that, you'll have compression forces, stresses that build up at the top, and then tension forces that build up at the bottom. And all of these are at the far extreme tops and bottoms of the beam. So you see here. So that's where those stresses are. So if you have corrosion in what we call the flanges, which are these tops and bottoms, versus the web, in the center of the beam, that's much more concerning than it would be at the end. So here's this right here is kind of your bending diagram, we call it. You see bending at the middle is the highest point, and then at the end is much less, right? So if you have damage to the flanges at the end, the flanges aren't as important at the end, depending on the connection, obviously, but in general, it's not as big of an issue as a large loss of the flange in the middle. And so conversely, the opposite is kind of true with the web. So the web of the beam is the vertical part in the middle. And a lot of that, what that controls or resists is what we call the shear, which is basically the reaction, the vertical reaction of the beam. So if you have a distributed load like this is our loading diagram where it's just even, the most of your reaction of shear is going to be at the ends where the beam itself is bearing on its supports. So at these points at the ends where the shear is the highest, you want to have the web be in the best shape. So if your web is corroded and has a hole in it in the middle of the beam, we want to address that obviously, but it's not as big of a concern as it would be at the end necessarily, especially if it starts to interfere with these connections and destroy these connections, which is very common. This is kind of one of the reasons sometimes you can kind of see, you'll see beams with holes in the middle that are purposely put there, or even joists, trusses, with the diagonal members, they're open at the ends. And that's for that reason, that they don't need the shear stress there. So when we look at these repairs, we want to address those. So you have here, you have a large corrosion in the web. I have a picture here with some corrosion on the flanges. And so when we see these localized damages, usually we can repair them, or the goal would be to repair these beams with plates to replace the lost, what we call cross-sectional area here. You can see here on this little side view, we've lost some area of the beam at the web and some at the ends. So we want to restore that area of the section, the cross-section of this beam by adding additional plates. Usually we're going to assume that the area of the flange, or this plate here that we're adding to the flange, is at least as much as the original, especially if the corrosion is very bad. So say, if this is 5 inches by 1/4, we'll want to use at least a 1/4 inch plate and go a little bit beyond. And then typically too, we'll do the same thing here, and we can do the same with the webs and weld those down. A lot of times that's welded. It can be bolted. Welding is much simpler, but sometimes environments at plants, welding is not allowed, so we have to figure that out. But we do want to try to restore that. So this is plates. Beams, if they're beyond repair, obviously replacement is always an option, and I think that's common with pretty much everything we're going to talk about today. But I think, in general, we're trying to avoid those replacements, especially for a lot of this stuff that's already loaded or has equipment on it that we can't remove. So we want to try to think about it in that terms. So with that corrosion and weathering, sometimes it's important to think about good housekeeping. A lot of what we see when it comes to wide flange beams or I-beams is buildup of debris on the members. Obviously, there's kind of some shelf space at the tops of the flanges where material can build up. This material usually will collect moisture and it'll sit there. It'll stay wet. The beam can't really dry, and that'll rapidly accelerate the corrosion that you're seeing. This is like a minute line. Something I like to always think about doing when I have a diagonal bracing member. Sometimes you'll see these members like this, like an angle or an L shape or a T shape. Generally, it's a good idea to keep what we call the stem, which is this part here, to have that turned down, or if it's an angle, to have the leg turned down so that there's not this shelf at the top. So you can see in this situation here, there's a nice little pocket here for material. There's a nice little pocket here for material to build up on, and that'll increase that corrosion. And as you can see here, that we've had some delamination, some spalling of the steel because of that. So columns, so vertical columns, we're thinking very similar to weathering steel. They're also susceptible to that, especially at the base plates, kind of like we were talking about before, where the material will build up on these base plates. It'll sit there, it'll be wet, and it'll rot holes in the flanges or in the web. Here's a good example of a hole right through the web, completely eaten through. Sometimes it does happen, up above. Just kind of, there's a chip in the paint or maybe some other damage lets the corrosion eat through, and then it just goes from there. It'll obviously without cleaning, it'll just get worse and worse. Repair methods for these are very similar to with the beams. Okay. But we'll add plates. We're trying to restore that section of the loss that we've lost with from due to corrosion, right? So if we're losing pieces of the web here, we're going to put a plate in there, and we're going to repair that and restore that. So typically that is the goal. You know, it's much easier to be able to catch these things early and put these plates in and not have to remove the column or replace the column. But sometimes that's required. So sometimes the repair cannot be repaired per that plate method. This is usually more complicated, replacing individual beams since the columns can't be unloaded. So this is an example of a project we did where we had a steel column from a pre-engineered metal building, big warehouse building. You can kind of see here in the picture, the bottom of it was almost completely eaten away, and it just couldn't be repaired. So we put some temporary shoring in. This was temporary, put in place to support the load of the whole rest of the building while the part of this column was cut off and a new bottom section was fabricated and welded in. So obviously this is much more costly than the plates, which is why we kind of talk about wanting to make sure that we catch these things early. Sometimes with weathering too, we'll see it in equipment, or bins. In this example, in this case, these bins had a rain cover on them. It was part of the original design, and the corrosion ate that out. It was very thin metal, 10 gauge metal. And unfortunately, once that happened, then it became a pocket where all of this material and water sat in here and then started eating out the actual stiffeners, these 5-inch channel stiffeners that were part of this too. So there's a lot of corrosion here, and we ended up having to cut these out one by one and replacing them, splicing them into places that weren't as damaged, and then replacing the rain guard almost completely. But sometimes this happens as well, so there's options to replace that. And I think in this case too, we also had some holes in the wall of the bin that needed to be replaced and patched. So moving on to concrete, weathering is also an issue for that. A lot of times what you'll see from the most damaging part of concrete at our sites from what we call freeze thaw. This is a phenomenon, I guess you would call it, with concrete where it's porous enough that water will get into the concrete. And then if it's warmer out, water will get in, then it gets cold, the water will freeze. Obviously ice takes up more space than the water. It pushes the concrete, causes cracking. Microscopic cracks form, that allows more water in, that cycle repeats, and you end up getting large chunks of concrete breaking out. You can see here we have some severe spalling where due to the freeze thaw that's happened. A lot of times to prevent this, if we know that a concrete mix is going to be used outside, we'll include air entrainment, which is kind of like almost like a detergent, like soapy bubbles. That'll put air pockets in the concrete, which doesn't affect the strength actually that much, but does allow for voids for the water to expand into when it freezes. So that's kind of a prescriptive method, but then once it's spalled like this, a lot of times. Yeah, so anyway, you kind of see here, there's a little bit of a chart, give you guys a chance to chance to review that. But yeah, so the spalling like this, this extreme can be, is usually repaired with the type of mortar. No, I'll show some of that in a second here. Also, so concrete will naturally crack during the hardening process if there isn't a sufficient amount of reinforcement included to resist that internal tensile force. It's normal, somewhat unavoidable, but also can be limited to a negligible amount with the proper reinforcing. But sometimes, if that's not the case, or even with those small cracks, water can get in. You have your freeze thaw issues, or maybe the cracks are big enough to where it's maybe a design issue and it wasn't reinforced enough. So typically, cracks like this will be repaired with a epoxy product. There's many different kinds of these. I have my favorites vendors. I don't want to play too much of your favorites. Josh just texted me, but you call them, and a lot of times they'll be able to select a product for you out of their catalog for the application that you want to use, right? So kind of on this slide here, each of these applications, horizontal on the ground, overhead, vertical, a lot of those will typically have maybe even will all have different products from the same vendor. Advanced, yeah, okay. So a lot of what I think you guys will also see at your sites are what we'll call like a corrosion or weathering or erosion from harsh chemical use in the manufacturing process. These can cause dissolve and erode concrete faster than normal weathering. These include any kind of acids, a lot of common ones: hydrochloric, sulfuric, nitric, even citric and lactic acid will do it. Salts, sulfates, sodium hydroxide, ammonia, even sugar and petrochemicals will eat at concrete. So if these kind of things are allowed to sit on floor surfaces for an extended period of time, you'll notice spalling, where chips of concrete will break loose, will get eaten away, will erode away. A lot of times these are prevented with a type of coating, but if not, different types of repair mortars can be used, which is like a kind of like a thicker, hardier concrete type material. And again, just like the epoxy, any vendor you talk to will be able to provide different types of mortars based on the application that you want to use. So if it's an overhead, like the underside of a slab, you'll have different things you can pour for there. Different floors. The floors can vary quite a bit too based on the thickness. A lot of the products will have different, minimum thicknesses up to like maybe even 1/8 of an inch thin that they say they can be put down without, chipping. You do want to contact either an engineer or a vendor specifically to find out what product works best for you, because nothing's worse than putting a whole new resurfacing on a floor and realizing that the product you selected was not specified for that level of thickness, and then it just chips away within a couple weeks or a year or whatever. And then there's even ones like this shotcrete here, which I think is always an interesting type of thing, where they just pretty much blow the mortar at the concrete and have it stick to it. Columns, same way. You'll see corrosion can if you have a concrete column against the ground that's or through your floor slab, and you have material sitting up against it that can eat it away. If it's outside, you can have freeze thaw damage. When we see these losses in the section, sometimes we'll do a full replacement if we can get the load off there. Other times, if it's like a large parking structure or like building, you'll see these column jacketing, where they dial in reinforcement and then attach that to the cage and then pour around it to thicken that up. And when we're doing concrete repairs, it is important to also notice that the moisture in the concrete will cause the corrosion of those bars. As those bars corrode and expand, they'll cause concrete to spall. And then when you make those repairs, it's important to clean the rebar and also use a rust inhibitor to kind of guarantee the quality of that repair. All right, so a quick poll question. You can think about it in your mind. I'll give you half a second, but corrosion in the flanges in a steel beam is more serious when located in the center of the span than at the end. Is that true or false? You guys just think about it. I'll give you half a beat. And so that is true. Right, good. Yeah, we want to make sure that we're watching for those we're watching for the repairs where the stress is the highest. Moving on a little bit more uncommon, but also troublesome is the impact damage. It's another type of damage we see quite often. Columns are a big victim of this, I would say. Fork trucks are the culprits quite often. Sometimes, if the damage is minimal enough, you can re-straighten column pieces, but typically it's too difficult and too costly. So a lot of times we'll do is encasement of concrete, which both stabilizes the damaged portion of the column against buckling, and also creates maybe a future barrier for anything kind of happening like that again. This is the same both for the wide flanges we just saw, or the eye-shaped columns, and then also for round and square columns as well. Sometimes you'll see those. You can encase those. And in this instance here, we had more minimum damage to a pretty large diameter column, so we decided to give them a couple options to reinforce it over the small buckled area or the damaged area. With like a slightly larger piece of tube or some stiffeners here. Concrete can be damaged too. There's a little corner here that looks like it's been smacked by a couple different fork trucks. That'll depend. The repair for that will depend on what that damage ends up looking like. If it's a crack, you can usually epoxy it. If it's a larger chunk that got knocked off, they might have to put a form down and repair it with a mortar. If it's significantly large, maybe even some additional reinforcement to dowel that in to hold that repair section in place. Anchor rods, sometimes when they're sticking out during construction, can be damaged. The ACI guideline that I mentioned at the beginning gives some guidance on this, where if the anchor rods are grade 36 and less than an inch in diameter and bent less than 45 degrees, they could maybe possibly be yanked back straight, but otherwise you either have to heat them to bend them back or to just cut them and start over with a drilled and epoxy anchor. So then the last part or next part would be of damage we see is the design deficiencies. So this could be something that either fails or we notice during a walk down that is not, that an engineer can look at it. Maybe it was something that was put in by a contractor or just maintenance person, and we'll notice that it's not sufficient or not up to code, and that'll be flagged, and maybe that'll need a repair. So right here in this first picture, this is a column essentially holding up a corner of a platform. This member here is about 20 feet long and is a 2x2 piece of tube. So it was a little undersized. It was enough to maybe hold up the platform here and one person, but not necessarily up to the design levels that you would need. We also have here, maybe a little harder to see, but at times we'll see is a guy wires for some type of process stack that are tied either to something that's not sufficient to support the reaction from them, and then also maybe tied incorrectly. I think this one here only has one buckle, which is not compliant. There's also situations here where we have accidental overloading. Maybe the the loading accidentally exceeded the design loading of it. So we'll have damage to a collapsed area of like a roof like this, and that'll have to be repaired. Those are all kind of case by case basis of what we can do there. But all these situations are something that an engineer would probably need to be addressing for you. When we have repairs, or when we do identify things like an existing member that's undersized for a new loading or an existing loading, we have reinforcement options. Generally, we want to look to increase the bending capacity of those members by additional steel, adding depth or some additional area. Generally, this is done by welding. So concrete can have some common deficiencies. A lot of that includes the insufficient clearance to reinforcement. So the distance between the face of the concrete and the rebar itself, if that's insufficient, which could be a design issue, it could also be a construction issue, because sometimes you try to have them, if the contractor doesn't necessarily have it exactly where you want it, it could be a little too close. So if that rebar is too close to the edge, it can get exposed to more moisture than intended, which leads to corrosion in those bars, which then leads to spalling or the concrete getting, popping off. Cracks, like this large one here in this column, can be caused by a couple different things. It could be, overstressed or undersized members, or some sort of settlement issue with the foundation. So we can kind of show here. I'll go into, if we have something like concrete, a lot of these if we're repairing a column that doesn't have enough bearing for the shear transfer from the floor slab or from the beams above, will increase the width or the diameter of that column to transfer that force better. If you have a beam, like this concrete beam here, if it's undersized and you need to strengthen, you can strengthen the tensile ability of it by either deepening it, adding more reinforcement, or this is kind of nifty where they add this FRP, this fiber reinforcement, these kind of tensile strands, essentially gluing those to the underside of the beam to increase its ability to, its bending capacity in that way. Sometimes bends will be, the design of a bend will be deficient. This could be the actual structure of the bend itself, or maybe some sort of process issue that caused damage. When that happens, we can do localized repairs, stiffening, kind of try to fix those damages. So then we have fire damage. The steel guide puts categories on these. I don't know if some of you know, but fire, increased heat will reduce the strength of your steel substantially. I mean, we've all kind of seen some of this stuff before, where as temperatures heat up, something that was originally sufficient for the load it will now be softened enough to where it'll collapse. The steel guides will put this in, when you're doing a fire inspection or inspection of a structure after a fire. We'll put those into 3 categories. One is members that were, maybe singed, burnt, have some fire, dirty. They're dirty, but are straight and relatively unaffected. 2, some that are partially deformed, but could be heat straightened. And then 3, like you're seeing, this would be more like category 2 of this melted brace right here. But then category 3, like this collapsed column, I mean, that's obviously severely deformed. It would need to be replaced or rebuilt. All right, so the last part of our repairs that we looked at are going to look at our non-engineered alterations. This is when a change is made without review from an engineer, or and turns out to be something that's not compliant. My favorite one, and I see all the time, is the partial removal of a cross brace. So a lot of guys probably have seen these X braces that are all over the place. Sometimes one piece of this will be in the way of maybe a piece of equipment or a pipe, and they'll cut it. The one thing you need to understand with these is when they design these cross braces, both sides are only designed for tension. So when you remove one, the other one is still good in one direction, but if the wind blows in the other, it doesn't have enough strength to take any compressive force. So you're essentially taking away half the support of your structure. If the brace can't be replaced because there is something in the way now, or a piece of equipment needs to go in, what we'll do is this repair kind of strategy here, where we actually take out all the bracing and replace the one that can remain with a larger member that is sufficient for both tension and compression. And then, something similar to that, or something also we see sometimes, is openings cut into walls, concrete or masonry. These need to be reviewed with the PE to determine the feasibility. This one was a load-bearing masonry wall and they cut a hole that was about 14 feet wide, and they put in a lintel, but it was just a small angle. So we needed to come in and reinforce the opening so that it would, stay up, essentially. All right. So last slide here is just I do have a white paper that I've written. I can email it to you, or you guys can scan this and download it, regarding structural assessments, which is something engineering firms can do. Basically, is a walk down of a site, either the whole site or partial site, to identify a lot of these issues that we've talked about today. See any kind of damage. We can generally, when we do, we'll create a list of all the items, and then identify which ones are the most severe and troubling, and also which ones need additional engineering, or perhaps could just be have a contractor come in and repair. So it's a helpful tool, and I think, and if you haven't read this paper, the white paper, it explains a little bit more than maybe I can right now.